Okay, we're going to learn how to solve linear systems algebraically. And we're going to use the idea of substitution. Now, if you think of what does substitution mean? If I gave you 3x plus 7 is equal to y and told you that x is equal to 4, because we have two quantities that are equivalent to each other, we can replace one with the other. So every place that I have an x, I am instead going to put a 4 because I'm going to substitute the 4 in place of the x. That then gives me an equation I can solve, and I get y is equal to 19. So that's the basic idea of substitution. Now this works even if I say, well, what if x is equal to a smiley face? So I have 3x plus 7 is equal to y. Well, I can replace any x I see with the smiley face. So I could do 3 smiley face plus 7 is equal to y, and they are equivalent expressions because x and the smiley face are the same thing. So what if I had instead x was equal to 2y? So I still have my 3x plus 7 equals y, but now x is equal to this 2y here, so I'm going to replace my x with a 2y. And I would then get 6y plus 7 is equal to y, and then I would end up getting y is equal to 7 over negative 5. So anytime I have one quantity equal to another quantity, whether it be a single number, another variable, or another expression, I can interchange them. So I can replace any x I see with 2y. That's what we're basically going to be doing when we solve a system using substitution. We are going to take a variable and we're going to plug it in somewhere else. Now some of them are going to be very simple, and what we always need to do is we always need to get a variable completely by itself. In this case, our top equation already has y completely isolated, so we don't have to do any rearranging or moving around. All I'm going to do is I'm going to take any place I see a y in my second equation, and I'm going to replace it with 4x plus 2. So I would have 2x plus 4, and then instead of y, I'm going to put in there that 4x plus 2. Now I have an expression that I can solve because I only have one variable. I only have x's in there. I need to distribute that 4 out. And now I just need to do some basic arithmetic to solve this. So I need to combine my like terms. I get 18x. Subtract off my 8. And then divide both sides by 18. And we get x to be 10. Now, what you have to realize is we have only found one piece. Because remember, when you have a system, what you really have are two lines that intersect, and we're looking for that point of intersection. Well, our point of intersection is always an x-y pair. I only have found one piece of my solution. So what I need to do now is I need to go and substitute this back in to either of my equations. It doesn't matter which one you pick. I'm going to pick the top one because it's a lot simpler. So I'm going to plug that 10 back in here for x, solve that out for y. Well, 4 times 10 is 40, plus 2 is 42, so I get y is equal to 42. So right now, I have a solution of 10, 42. The nice thing about this is you can always check them. So I'm going to plug that back into my top equation. So I would have 42 is equal to 4 times 10 plus 2. Solve that down and I get 42 equals 42, so it works in my top equation. I'm also going to plug it back into my bottom equation. So I would have 2 times 10 plus 4 times 42 equals 188. And I get 188 is equal to 188. So since it worked in both equations, this is the solution to my system. Okay, so here's another one. Use substitution to solve. Now this one is slightly different because I don't have a variable isolated. What you want to do is you want to figure out, well, which variable is going to be the easiest to get by itself. So you want to think about which one has the least amount of stuff to get rid of in order to get it by itself. And what I mean by that is if I look up here at the m, the only thing I have to get rid of is the r. Or if I choose the r, the only thing I have to get rid of is the m. So those two are about the equal as far as hardness to get rid of. If I look at my second one, if I want to solve it for m, I have to get rid of the 8r, but then I also have to get rid of the 3. A little bit harder to do. It's still doable and it will still work, but it just takes a little more time. If I want to solve this one for r, I would have to get rid of the 3m, and then I'd also have to get rid of the negative 8. So again, it takes a little bit more work. So I'm going to take this top equation and I'm going to solve it for one of my variables. I'm going to solve it for m. Well, in order to do that, I have to move the r to the other side of the equal sign, and I do that by doing its inverse, so I need to subtract r. So I'm left with m is equal to 10 minus r. Same equation, just rewritten. Then I'm going to use substitution because now I have this variable isolated. I can replace any m down here in my equation with 10 minus r. So I would have 3, and then instead of m, I'm going to put my 10 minus r. Now it's critical that you use parentheses because it's 3 times m. Well, this whole thing, this 10 minus r, that entire thing is your m, so you have to take 3 times the whole thing. And in order to do that, you have to use those parentheses. And now again, I am down to an equation that has only one variable in it. Distribute my 3 out. Combine my like terms so I can combine my r's. And it's negative 3 and negative 8 would give you a negative 11r. Subtract off my 30. And I have negative 11r is equal to negative 38.5. Now I need to divide both sides by negative 11, and when I do that I get r is equal to 3.5. That's only part of my answer. Now realize that this isn't x and y, but it's an m and an r, and since they're variables you could technically use any letter to represent them, so it's the same concept. I have r, I still need m. So I need to go back and I need to plug it back into something. I'm going to plug it back into that equation right there because it's the simplest one I have. So I'm going to get m is equal to 10 minus my 3.5. And when I do that subtraction, I get m is equal to 6.5. So now I need to go back and I need to check it. So I need to see, is m plus r, so is 3.5 plus 6.5, is that equal to 10? And I get 10 equals 10. So it works in my top equation. Then I need to check my next equation. If I take 3 times 6.5 minus 8 times 3.5, I need to get back a negative 8.5. Well, when I take my 3 times it by 6.5, I end up getting 19.5. Minus, when I take that 8 times that 3.5, I get 28. And when I take that 19.5 minus the 28, I get negative 8.5 equals negative 8.5. So that tells me that my solution is right. Now for this one, since we don't actually know which one is our independent variable and which one is our dependent variable, it could be a little bit hard to write it in an ordered pair. So what you could do is you could say m comma r would equal 6.5 comma 3.5. Or let's say you wanted to say r was your independent variable. You could do r comma m is equal to 3.5 comma 6.5. Now when it's x and y, we don't have to do this front part because it's automatically assumed that x is first. But if you have different letters, you can write it like this. Or you could, for this particular case, you could leave it written out as r equals 3.5 and m equals 6.5, because that would still give us our solution. Okay, we have a second one now. So I've got 2x minus y equals 50 and 7x plus 5y equals 250. This one looks like my y value is probably going to be the easiest thing to solve for, so I'm going to subtract 2x from both sides. And that would leave me with negative y is equal to 50 minus 2x. Now it's not okay to keep this negative sign right here. I need to divide everything by negative 1. and that will give me y is equal to a negative 50 plus 2x. So that's going to be my modified equation. So now in the second equation, every place that I have a y, I'm going to replace it with negative 50 plus 2x. And remember, you have got to use those parentheses. Now that I've got it substituted in there, I can go ahead and start solving it because I'm down to one variable. Combine my like terms. And now I have to add 250 over to the other side and divide by 17. This one we can leave as 500 over 17, it doesn't reduce, or we can divide it out and get the decimal format of it. Since it's a non-repeating, non-terminating decimal, I would prefer to leave it as a fraction, because what's going to happen is if you round it, when you plug it back in here to solve it for y, it's going to not come out right. So I need to leave this as a fraction. If this had turned out to be a terminating decimal like 2.4, then it would be okay to use the decimal. But this turns out to be 29.4117, and it just keeps going with no pattern. We cannot round it. It will not give us the right y value. So now I'm going to plug it back in and see what my y is. So y is equal to negative 50 plus 2 times, and I plug in my x here, 500 over 17, and then I can solve that out. Now remember, in order to add fractions, you have to have a common denominator. Well, my common denominator for this one would be 17, so I need to multiply the top by 17 and the bottom by 17. So I'm going to have y is equal to negative 850 17ths, because that's what negative 50 turns into, plus 1,000. And now I can subtract my tops. Oops, there's a 17 under there. And I get y is equal to 150 over 17. Now you can check again to see if the decimal is going to be anything decent, but it's not. It turns out to be 8.823, and it goes on and on. So I'm going to leave mine as fractions. So now, since this is an x, y, I'm going to write them as an ordered pair. And I don't have to specify that x comes first because it's assumed that x is first. So my solution is 517ths, comma 150 17ths. I need to take that and plug it back in to make sure it works. Now this might be a case where it's going to be quicker to use your calculator. So you can type into your calculator 7 times 517ths plus 5 times 150 over 17, and you can see what that's going to give you on your calculator and then compare that to the 250. When you type that in, you get 250, so it works out there. You can do the same thing for that top equation. You can type it into your calculator right here and take the 2 times the 500 over 17 and subtract the 150 over 17. When you do that, you get 50, which according to our original equation is what we needed. So it does work in both of them. So our solution would be right. Okay, so here's a practice problem. I want you to pause the video, see if you can use the substitution method in order to solve the system. Start by picking a variable to isolate and then substitute it into the other equation to find out what your solution will be. Okay, you should have ended up getting 4, negative 3 for your solution. I started out by isolating my y. I plugged it in, went through the algebra steps and got my x to be equal to 4. Then I took that and I plugged it back in over here, went through the algebra steps and got my y to be negative 3. So I had a solution of 4, negative 3. Then I came over here and I checked it. I plugged it into my top equation, plugged it into my bottom equation. They both worked out, so 4, negative 3 ends up being my solution to this particular system.